Hello. So we are considering a linear relationship only. So you have to imagine a trend line going through the dots. And then how do we interpret the scatter plot? So first, think about these three scatter plots. The left one has a obvious downward sloping trend line, and in the middle there is no. My intention was there is no clear trend. It could be flat, or you can think it as a little bit downward sloping or a little bit upward sloping. Uncertain, it's more like there is no trend. And on the right example, it is a clear upward sloping. So the direction of the relationship is about slope, where it goes. So it's more flat, assume it's flat. And that's the direction, slope. The sign of the slope is about the slope direction. And strength of the relationship is about the tightness, how much the deviation, the distance from the trend line to each observation. So when you compare these two, it's clear. On the right, if you imagine a trend line going through these observations, then clearly the relationship is very strong because it already nearly makes a perfect line. So if it was a perfect line, so if all the points lined up in a perfect straight line, that is the strongest possible linear relationship. But as the observations deviates from the trend line, you are going to see something like this, more noisy trend. Trend is the same, basically trend is the same, but on the left there is more errors or more noise, more deviations, and relationship is weaker. So that's the difference. If you imagine even more spread out observations, that implies a weaker relationship between them, right? These are basic framework we are going to work on, and we are going to, so it's just eyeballing the graph, but we are going to quantify these ideas. How to find the trend line, how to find the slope, and how to think about the strength. So let's go. The first idea is, remember, we are going to find the slope, and the first step is to find the center. Let me use the mean as the center again, and it's not a big assumption. So and suppose that the center is here. So the vertical horizontal line is the center. The mean of 4 is the mean of y. Y variable is on the vertical axis. And suppose that 4 is its mean. So we draw a line there. And x-axis, horizontal axis, variable x is on the horizontal axis, and its mean is also 4, and we draw a vertical line from there. So then this point, the crossing point, is the middle of the two variables, exactly at the center of two-dimensional distribution. And from here, I'm going to split the plane into 4 quadrants, and what we are going to do, what we'll think about here is on the top right panel, top right quadrant, the first quadrant, we are going to interpret this as, so they have x observation greater than its mean, and y is also greater than its mean. So I would interpret this. So for example, observations on the first quadrant have x increase from its mean. So when x increase from its mean, if observation goes to the right, then observations in the first quadrant have higher, also y increase from y bar, the mean. So when x increases from its mean, y also increases from its mean. So in the end, they are going to be located in the first quadrant. So they represent some, if there are more like dominant number of observations live here, that means there is more likely to be increasing trend, like upward sloping trend. Same thing happens on the other side. So on the third quadrant, when x decreases going to the left, y goes to the bottom, go down. So these observations imply x decreased, so y decreased at the same time. So again, the first quadrant and the third quadrant imply that the trend line is likely to be upward sloping. If more observations are there, then it will be upward sloping. If there is, by the way, however, if there was a downward sloping line, then there would be more observations on the fourth or on the second quadrant, right? If there was a downward sloping line trend, then you would see more observations here and here, because when x increased, y should have decreased, and when x decreased, y should have increased. So let me put it this way. If the trend was increasing, upward sloping, there would be more observations on the first and the third quadrants. However, if the trend was downward sloping, you'd see more observations in the second and the fourth quadrants, right? It depends on the direction of the relationship. So then, how do we quantify that? So let's quantify that. Our idea is the first and the third quadrants have these properties. So say xi minus x bar this is how much x increased from its mean, and yi minus y bar is how much y changed from y bar. If their signs are the same, if both changes, change in x and change in y, have the same signs, then they would be in the first or in the third quadrant. So their product, if you multiply them, you are going to see positive number, right? This is how we characterize these guys and these guys. We are going to use the signs of their products, multiplications. On the other hand, the second and the fourth quadrants have different signs between x and y. So if the change in x is positive, the change in y would be negative, vice versa. So the signs will be different. When you multiply them, you are going to have a negative number. So these observations and these observations in the second and fourth quadrants will have a negative product, negative sign from their product. That's the intuition. This is how we are going to numerically characterize the idea. Then we can define covariance using that idea. Covariance is the average weighted sum of the cross product of deviations. The deviations is like x deviation is xi minus x bar, and y deviation is yi minus y bar. So you cross product, make up cross product between them, and take average. Sum the products, and divide by sample size -1. Why do we use -1? The idea is exactly same as the sample variance formula. When you use -1, it will be unbiased. So that's why we use sample covariance or sample covariance formula, but not a big problem here. I'm not a big problem. Okay, one more to say here. So remember, the deviations xi and yi must be from the same country. I is one observation, and of course you have to multiply two deviations from the same observations. You cannot multiply like USA GDP to Mexico's temperature. That does not make sense. So your data must be paired. You should know which variable is from which country. And And this form is actually a generalization of variance. That's why it's named as covariance. So consider covariance of x comma x. So in fact, y equals x. So in your Excel, you make a column for GDP, and you copied and pasted the same variable right next to it. So you have two columns. So in that sense, you have two random variables. Then you should be able to calculate the covariance. If you do calculate that, then y equals to x. So yi should be xi. Y bar should be x bar. So xi minus x bar times xi minus x bar. So it's just squared deviations, which is this guy, right? When you replace y with x, this covariance formula simply becomes a variance formula. Of course, denominator maybe n or n minus 1, but just that's your choice. So in that sense, the variance can be viewed as the covariance between x and x itself. So variance is just a special case of covariance, right? So in that sense, covariance captures the deviations. It's more about deviations. Okay, I am going to consider this example, simpler example, numerical example, in the next video. So see you in the next video. Thank you for watching the video.